Okay, my friends, you know I am heavy into chemistry and biology and all that. And what is this? Bioorthogonal chemistry. It's biology, but everything is chemistry. So biology has to happen really quick. And it happens, as I've been saying, right along with transition metal elements, basically. They are the things that drag around the molecules through your body that attach and detach using oxidation states primarily. Now, what happens with molecules when they attach and detach? They're talking about click chemistry, where they can make a whole batch of stuff happen really quick by just putting the two of them together along with copper sulfate. And I'm going to talk about copper in a second, but here's all it is one molecule is going to have a positive charge and one's going to have a negative charge hanging off somewhere. And when they come together, they click together. Now, what will happen then is a whole bunch of entanglement will occur, and they'll fold and do all these kind of things as what's called a protein. But you can't do this with the standard model. You have to use electron flood theory, which says everything's a dipole. That's why they click together. They click together because one's a positive, one's a negative. Okay, I mentioned electron flood theory, and I have found the same particles they found at Fermilab and CERN. And here's what it boils down to. One of them is a bowling ball, has no energy other than gravity and dark matter. And it's heavy and hard. This one's puffy and glowy and is energetic. But they are dipoles, and the two of them together make what we would have always considered an electron. But it has a dark side, which is the muon. I go through this in very, very deep detail. Now, this talks about the same particles we found, and let me show you those particles. All right, my claim is that every particle there is consists of those two glued together. They call it a gluon. That's the muon neutrino, electron neutrino. Together, it's a gluon. If you separate them, that would be called a sterile muon, and that would be called electron shower because it showers. And here is that actual event occurring. Normally, the two of these together are back to back, make a photon. That's what we did. We took light. We didn't take protons, we took light and accelerated it. Now that's normally what it's supposed to be like that, attached together. The black one is the bowling ball. The white one is the shower, and it pushes and shoves and explodes. And this one you can see, I hope you can see that little glowy particles in the front there. It's concussing with those particles. So they're glowing, it's glowing, and they're getting energetic. All right, now, again, this is what it's supposed to be like, and they never separate. They are glued together very tightly. However, what we did was through the Venturi here. When that happened, all bets are off. They separated. The black separated from the white. That means fission. Back together means fusion. And here it is right here. And that's, nobody's contesting this. Nobody's contesting it. The muon neutrino was attached to the electron neutrino. We saw that, the black and the white. And then the muon becomes a sterile muon because of Cherenkov radiation, which happens because it enters another medium, which is what we did. And the white one goes on its way as a shower, which is what happened. Now, they want to be back together, so instantaneously they come back together, and they know that as well. They know, they claim they know exactly how long they separate out. It's in nanoseconds, billionths of a second, and which is true. This is light, and that's the distance from the Venturi, and it's like only about that far. This is very highly magnified. Now, we can see that we had accelerated the particle, which was that four-banger particle, and here's where it's separated, fission, and here's fusion. So and again, that's it. I mean, how more simple could it be? A proton is 1,835 of these electrons. The two together make an electron. So there's 1,835 of these particles make up a proton like this. If there was 1836, it would be a neutron. And if you look up the weight between a proton and a neutron, it's one electron. It's like 0.0005845, something like that, atomic mass units, which is one electron's worth, which is exactly what the difference between a proton and a neutron is. It's hard to believe it's not been understood. And you cannot make the complex chemistry of proteins and all the things of life with these just, a couple of these little balls touching together, that are just big balls. No, there are bazillions of these particles together. And when they attach in such elegant ways to make such unbelievable molecules. And that's what proteins are. All right, one of the researchers here, one of the three that received the Nobel Prize, was also a Nobel Prize winner, the only one that ever won twice, as he just said. And he worked on sterility, on catalyzed oxidation reactions. Catalyze means real fast. Oxidation means oxidation states, and they change oxidation states, and magnetism just changes instantly, so you get enormous amounts of changes in reactions, and literally hundreds of thousands of molecules per second are changed into a new substance because of this catalyst. And this catalysts are primarily enzymes. Enzymes only come from bacteria. Bacteria create enzymes, and they are chemistry sets, and they end up creating a specific product that your body needs to work on. Let me show you what an oxidation state is and how metal complexes carry things through your body. For iron oxides, iron is your blood supply. Hold on. All right, you see all these different colors? And all these different +2s and 3s and 4s and all that different stuff. And you see iron down here? That's your blood. There's a +2 and a +3 state of oxygen. That means there's 3 extra oxygens, and this has 2. That one is expended blood, the vein blood, and this is the artery blood. Now, they're showing these colors, and that's not what they are in your body. The vein blood looks bluish, and the red, real bright red blood is the artery blood. Now, you take these metals. All these are different metals: magnesium, iron, cobalt, copper. Copper's a real key player here, which we're going to see in a minute. But look at vanadium. It's got all kinds of different oxidation states, chromium. These are in your blood. All that stuff is in your blood, 100%. And I can prove that, and I will in a second. The center core forms the complex. And you always have, it's called aqueous. See, aqueous solutions. That means there's a lot of water. And she's going to be talking about this because, oh boy, now we can do it in water. Well, we can do it in water forever. Now, all of these are water molecules that surround, but they have attachments to them that are called ligands. So let me read this to you. Transition metals form colored compounds and complexes. That's these transition metals. These colors can vary depending on the charge on the metal ion. These are the metal ions. An ion means it's got extra or not enough electrons. The number and type of groups of atoms called ligands attached to the metal ion, all right, in aqueous solution, ions form complexes with colors shown to the right. So what happens is they're given and taken these oxygens, and they're moving products through your body using these metal complexes. That's what, in these aqueous solutions, they have to flow. And when they pass something, they say, oh, I'll take some of that, I'll take some of this, I'll give you some carbon dioxide, you give me this chrome, or whatever it is. Now, electrons are arranged around the nucleus. Yeah, you don't have to know about this. And now I'm going to show you, I'm going to prove to you that that is what is in blood. You see that? That's a heart washed out. They did surgery on him. I guess the guy didn't make it, but well, whatever. These are the ventricle walls. These are the heartstrings, aorta, all that business. Tubes running through here, and a lot of fiber, and a lot of, the outside is the membrane, which is the fascia. Let's see if we can find that in opal, because opal is, if you saturated that in blood for hundreds of years, what you'd have is nucleophilic substitution. It would substitute everything in there for the stuff that was in the aqueous. It would have to be in a watery area and a lot of blood with all these metals. Then they would find the material that they want to bond with to become stable. You see that whole thing right there? You see that color? That big, that's a muscle. And you're going to have all kinds of different chemistry. You see the whitish looking stuff, the brownish looking stuff, different types of look to it, different types of texture to it. That means it's different chemistry. You see this? This is an opal heart. And it's sliced across and opened up. Now, you see the different colors. You saw the heart I just showed you. These are the walls that have turned blue. They want to be blue because the specific chemistry of this specific tissue wants to take on, let's say, copper. And if it can find some copper to attach to, it turns blue, as we saw those different colors. And it will, because it's in watery solution. It's just continuously being saturated with these ligands. And if they find something they can attach to, snip, done. And they turn this color. Now, red is the plasma, the blood, the red iron. Now, all these different little colors are all different little transition metals. And this thing was laying on its side this way. That was down. And that's why the metals are heavy and they fall to the bottom. That's at the top, the plasma. These are like the fascia on the outside. See, that's almost like feldspar. These big heavy-duty tubes. And the outside is going to be a membrane. These are basically membranes too. And the other ones are tissues that have to do all kinds of different things in there. They have jobs to do. All right, so that's why this is so interesting, because he worked on oxidation states too. And now they're talking about the periodic table and this click chemistry. And until they realize that the molecules that they're looking at are not made out of big gigantic plus protons and little tiny negative electrons. They're made out of dipoles. And until they realize that, I don't care how many Nobel Prizes you give them, it's never going to be right. All right, so here we are back again at the professor who has had the Nobel Prize twice. And this is Periodic Videos, is the maker of this video. And here it is. He's going to be, well, I'm going to just let it play.
Prize for chemistry twice.
Initially, I'm just going to add into this tube here the copper sulfate. So this is...
Did you hear what he just said? Copper sulfate. Copper, that's the key.
It's going to be our catalyst for the reaction.
It's the
Click
catalyst.
chemistry is an area of organic chemistry.
Organic means we're talking about biology.
It is slightly ill-defined, but what it is a way of doing chemical reactions very efficiently and very rapidly.
That is exactly what an enzyme does. Now, I'm not sure exactly what they are doing, but they are this click is these magnetic interactions. And I'm going to show you how a protein changes and flips and so forth based on catalysts and enzymes. Because an enzyme is a catalyst, and that's all we're talking about is catalysts. Let's see what else he has to say here.
Because it means you can even do these reactions in water, which for us chemists is often very, very difficult.
All right, the stuff I was just showing you is made to be done in water, aqueous solutions. Oxidation.
Water is quite reactive itself, so you can do these reactions in water. They're very efficient, you get very good reaction outcomes, and as I said, you generate no waste, which is great because we're interested in sustainable reactions that don't generate a lot of waste.
So you've 1.25 microliters into there.
Organic chemists often construct the most beautiful molecules by a whole series of reactions which are quite slow, the reaction.
All right, this is what he's talking about. You can change molecules, but when you just do it a little bit at a time, it takes forever. Catalysts are designed specifically to do this instantaneously. Okay, you should come up and watch this. This is fabulous. It's called Copper's Surprising Reaction to Strong Magnets. Force field motion dampening. Well, what does that mean? This is by Nighthawk and Light. Very, very well done. This is a dense, huge chunk of copper. Now, copper has a specific thing about it where it holds huge quantities of electrons in a cloud surrounding it. All right, copper is just saturated with electrons. And what do electrons do? They push and they shove. And what is a magnetic field? It's a huge cloud of electrons. And this is one of these heavy-duty magnets. So we've got our own pushing and shoving cloud, and we have another huge pushing and shoving cloud. If you let that one slam into that, what do you think would happen if they were both clouds and pushing each other apart? It would just, watch, here's exactly what happens. Where do you see this? This is, again, a big heavy-duty magnet slamming into something that has a huge magnetic field. If you let that slam into a glass wall of glass or anything and smash right into it, nothing would stop it. But watch this.
Of copper like a wrecking ball. The magnet
Boom.
loses all of its momentum at the very last moment in a way that almost looks supernatural. It reminds me of a scene in the second Matrix movie where Neo stops bullets in midair. What's really happening is of course the same thing that has happened in my other examples.
Okay, you can come up and watch this. All I wanted you to see was that there is an interaction between the two that can only be explained by a cloud pushing apart. So this has to have a huge amount of extra electrons, and this is trying to slam in, but its field is just pushing against it, just like a pillow to a pillow. And they just stop. All right, I'm going to show you something really cool. All bacteria create enzymes, and enzymes are catalysts. And these enzymes are like long chains, and then they coil up into things. Now watch. These oppose each other. You see it? They won't go together. All right. Now, an enzyme is just the opposite. It snaps like together. That's why they're talking about this click chemistry. And it happens, brrr, it just goes like crazy instantaneously. Now, let's talk about these bacteria, enzymes, and chemicals. All right, let's just run through this real quick. Bacteria are living cells. They're little tiny single-celled organisms. They have the capability of consuming wastes, reproducing, actually producing enzymes. Enzymes, I'm going to show you what they do. Better said, bacteria are the factories that produce these enzymes. When the right bacteria are present in the right quantities or in the right conditions, they produce enzymes much more economically than people can manufacture them. This is exactly what they're talking about, click chemistry. Enzymes are not alive. They're little chemistry sets. Now, whether they figured out how to make the little chemistry set or not, I don't know. But the bacteria know how to do it. They're complex, very complex chemicals produced by bacteria. They cannot reproduce by themselves or actually consume waste by themselves. They're chemistry sets to go out and make an interaction. They speed up chemical reactions without getting used themselves. They're just like a little trigger. However, enzymes are all proteins. And when I'm going to show you what a protein is, you're going to flip. Some enzymes attack proteins because they're made to break them down. You can't have all this stuff just floating around forever. So it's something that's called apoptosis normally with cells. It goes and kills the cells and then eats them. And they do the same thing to proteins. Therefore, enzymes' usefulness is limited by digestion from other enzymes. Well, here's the key. They're living cells. They produce enzymes. Enzymes do the chemistry. All right, every enzyme is a protein. You see this? It's nothing more than this. And they snake around like this, and then all of a sudden they'll go brrr and fold up. Now this one here, again, these two don't want to be next to each other. But if you change the chemistry of it, and you go some like that, now it clicks together. Then all of a sudden it does this and this and this and this and that. And you end up with something like this over here, which they're all like that. They're all extremely elegantly folded up. That's what proteins do. But originally they squirt out like in a big long squirt, and they were done. And that's because of a catalyst, and a catalyst is an enzyme, and an enzyme is because of the bacteria. I'm going to show you what catalase does, and this is what happens. To protect the body makes catalase. It's an enzyme that decomposes hydrogen peroxide before it can form hydroxyl radicals, which destroy tissue. Well, it's an enzyme. Enzymes are created from bacteria. So you have to have the right bacteria or you're not going to have the enzymes. All right, this is the crazy Russian hacker. I did this a couple months ago about the catalase and how it attacks blood oxygen. Now watch this. Here goes. Peroxide. Look at it foam up like that. Now, if you put tons of blood in there, it's just going to go crazy. See that? I see that. And that's what I was showing you out of. They've got. I believe there were probably 3,000. All right. Now, what I showed mine back here somewhere, which my samples, and I showed them foaming up back here. That was a spot I had to try scraping into to get some blood. And then I put well, here it is right here. See it all foaming up? Instantaneously. Look at that sucker bubble. It's the same exact. That's a blood vessel. I never expected such excellent results. That's just phenomenal. And that was out of one of these, I think it was out of Caesar's neck. I'm pretty sure it was right out of Caesar's neck, right there. This is Caesar Augustus. One side's flat, the other side is just a goose. And that's his neck. And that's where the artery was. And it foamed like crazy. Let's come up to where I'm coming up at it. All right, let's look. Looking right here in the microscope, you see it up there? I scratched it all up, digging the blood out of it and looking at it all different kind of ways, but I never realized I could do this with this hydrogen peroxide. It's really fabulous. Now watch this. Let me get it soaking in there, because it appears to take a minute or two to get it going. It does take about a minute, less than a minute to really start foaming, but watch. Oh, wow, look at that. Instantaneously. Look at that sucker bubble. Look at that bubble. Roger is excited. I never expected such excellent results. I mean, if that doesn't show you that the catalase is attacking blood, I don't know what does. Because I tried it in other spots where there was no real blood to speak of. This is just saturated. That's an artery. Okay, my friend, Spunky Sugar said to get a hold of Professor David Martell, because apparently he claims that the Loch Ness Monster is plausible because of some recent finds, and I also agree with that. And he is in the exact same interest I'm in, biology. Well, it's just biography, but his input to paleobiology and how soft tissue, well, here's right here, work concentration mainly on phosphatized soft tissues with high fidelity morphological resolution, investigating chemistry and rate of process, comparison with recent material and actualistic experiments. All right, I have the actual preservation. It is the preservation of fossil soft tissues, mechanisms, and paleobiology, exactly what I do. And I have figured it out. I understand it quite well. And I understand the fascia, which creates the feldspars, and then the internal parts change basically based on what the chemistry and how much water they're in and what the chemistry of the water is. If they're near a kidney or something, they're going to have a lot of salts, perhaps. If they're near, anyway, it's all related to the conditions that they were entombed in, basically. And the stuff I have pretty much was all from the big nasty flood. And there's gigantic things that nobody's ever considered. Now, will he engage? I hope so, because this is the kind of person that has the credentials to make discussions now. So, Professor, I certainly would like to speak with you, my friend. University of Portsmouth.